So, we are discussing about modular polynomial arithmetic, and in the last lecture we have seen that how z p to the power n forms a field under modular polynomial arithmetic. We will continue this lecture with another example, since we started our discussion with an example that Z8 forms a ring, but not a field, because under Z8 multiplicative inverse does not exist. We have seen Z7 because 7 is a prime number, so it forms a field. Now, this example will show that Z8 under normal modular arithmetic it does not form a field, but Z8 under modular polynomial arithmetic it forms a field, and we will show this thing. So, we continue our discussion on modular polynomial arithmetic. So, we are considering the example of we are taking it is Z2 to the power 3, because we want to show Z2 to the power 3 Z8 forms a field under modular polynomial arithmetic. Okay. So, first we have to take the set of polynomials. Again, what are the we see the set of polynomials, since it is p to the power n, p equal to 2, n equal to 3. So, p equal to 2 is p is ZP is 0 and 1, because it is Z2. Okay. So, I write it is Z2 is 0 and 1, n equal to 3. So, the polynomials are f x is of the form a1 x square, a2 x square, a1 x plus a0, and earlier we have seen already this set of polynomials S. If I consider the set of polynomials S equal to 0, 1, then x plus 1, x plus 1, then x square plus 1, x square plus x. Earlier one example we have seen that already, we have read this part, that how we get the full set of polynomials, because this is nothing but all possible combinations of a2 a1 a0, where a2 a1 a0, a2 a1 a0 all are elements of 0 and 1 Z2. Okay. So, now this is my set of polynomials, and we have to show that under modular polynomial arithmetic this thing. So, I need a polynomial, irreducible polynomial. So, what is my irreducible polynomial? Mx, we have last class we have defined the irreducible polynomial of degree 3 here, because my degree n, say n equal to 3 for this example. Now, there are two irreducible polynomial mx. There are two irreducible polynomial of degree 3. Of degree 3, and there I can write one is m1x, what is 1 plus x cube, another I can write m2x is 1 plus x square plus x cube. So, I have to choose any one of these. Let we choose the m1x, we consider m1x, and we start to form the addition table and the multiplication table. So, first we form our modular. So, first we our mx we have chosen, mx is 1 plus x cube. Okay, I write later. Since I have polynomial 0, then I have polynomial 1, I have polynomial x, I have polynomial x plus 1, I have polynomial x square, then I have polynomial x square plus 1, I have polynomial x square plus x and x square plus x plus 1. These are my 8 polynomials. First I do the addition, and we are considering the mx is 1 plus x cube. Now, I have 0, 1, x plus 1, these are my elements of the sets, the all polynomials, x square plus 1, x square plus x and x square plus x plus 1. So, here I have to do modular addition. This becomes 0, 1, x, because already we have seen additive identity is 0, x plus 1. So, we will be getting the polynomial only x square plus 1, x square plus x square plus x plus 1. If it is 1 plus 0, 1 plus 1 modulo 2, since my it is Z2 is 0 1. So, modulo 2 addition. So, this becomes 0, this becomes x plus 1, this is x square plus 1, this is x square because 1 will vanish, this becomes x square plus x plus 1, this becomes x square plus x. If I add x, this becomes x plus 1, 0, 1, x square plus x, then x square plus x plus 1, then x square, then x square plus 1, x plus 1, x, no x will vanish because x plus x 0, again this becomes 0, then x square plus x plus 1. Now, x plus 1 plus x square plus 1 means 1 will vanish, x square plus x plus 1, x will vanish, x square plus 1, and this becomes x square. First, again the similar way I can compute the sum. This becomes 0, this becomes 1, this becomes x, this becomes x plus 1 because x square plus x square 0. This is x square plus 1, this is x square, this is x square plus x plus 1, then this is x square plus x, this is 1, this is 0, this is x plus 1, and this is x. Now, if I add x square plus x square plus x plus 1, then x square, then x square plus 1 because x will vanish. Now, x, then x plus 1, then x square plus x will be 0, x square plus x, this will be 1. Now, x square plus x plus 1, x square plus x square plus 1, now x square, now this becomes x plus 1, now this becomes x, this becomes 1, this becomes 0. So, we observe some properties here. See, the first thing is all the rows, if I consider that they consist of all the elements of the set. Every row, that means 0, 1, x plus 1, x square, but in different order it is there. Now we see the additive identity, 0 plus 0 0, 1 plus 1 0, x plus x 0, because we are taking the modulo 2 sum. So, additive inverse exists. If it is first thing is this is additive identity. So, I write additive identity is 1, sorry, additive identity is 0, and additive identity that is 0, and then if I take the additive inverse, there must be additive inverse. So, I get 0 plus 0 0, 1 plus 1 0, x plus x 0, that means additive inverse is the element itself. So, additive inverse of x is x itself, is x. And see, this is a closure property, because already we have seen that table contains only the set of elements of S, only those polynomials. And since I got the additive identity 0 and additive inverse, and again it will be associative and closure, then commutative, all the properties will be satisfied. So, under modulo addition, that modulo mx addition, it satisfies all the property. Now, if we consider the modulo multiplication. So, we write that this is our addition modulo, addition table modulo mx addition table. Now, we consider the multiplication table. So, I consider multiplication. I have 0, 1, x, x plus 1, x square plus 1, I have x square plus x, and I have a x square plus x plus 1, the all set of polynomials. Then I have zero, sub 0, 1, x, x plus 1, x square, then x square plus 1, and I have x square plus x, and x square plus x plus 1, x square plus x plus 1. Now, I write my mx, because this time I have to take Rx, mx equal to 1 plus x cube, and I have to do here, since it is multiplication. So, I have to take the Rx, which is f x into g x modulo m x, and here my f x and g x it belongs to S, where S is the set of all these polynomials. So, S is 0, 1, is 0, 1, x, x plus 1, x square plus 1, x square plus x and x, all 8 polynomials x plus 1. Now, if we do the multiplication modulo mx, then 0. So, it will be 0 only, because 0 multiplied by any polynomial is be 0. Now, it is multiplied by 1 only. So, the polynomial itself if I multiply with x, now this time I if the degree of the product polynomial is more than 3, then I have to take the remainder. So, x into 0 is 0, x into 1 is x, x square, so less than x cube. So, x square I put, this is x square plus x, this is x cube, now it is x cube. So, I have to take the remainder. So, that means x cube divided by 1 plus x cube, and we have seen that is nothing but x plus 1. Now, again x into x square plus 1. So, it is x cube plus x plus x, and this is x cube plus x is there. So, it will be 1 only. Similarly, x cube plus x square. So, now if I divide x cube plus x square, so this becomes x cube will vanish, but x square plus x plus 1. Now, this becomes product is x cube plus x square plus x. So, this will be x square plus 1. So, now I have to take the remainder. So, similarly, if I compute that, this will be 0, this is x plus 1, now x square plus x, now x plus 1 into x plus 1, earlier we have seen this is x square plus 1. If I multiply and then take modulo mx, then this is x square plus x plus 1, it is x square, then it is x plus 1 into this becomes 1, and this becomes x only. Similarly, we can for x square into 1 is x square, this is x cube. So, divided by this becomes x plus 1, again x plus 1 into x square. So, x cube plus x square, x cube plus x square, I can do the divided by this. So, x square plus x plus 1, x square plus x plus 1. Now, x 4, x to the power 4, if I divide, then x 4 plus x square plus 1. So, this becomes x square plus x. We can do quickly here that x square, and if it is x to the power 4, just if I see that x to the power 4 and I divide it by x cube plus x plus 1. So, it will be x only. So, x to the power 4 plus x square plus x. So, this becomes x square plus x. So, we write x square plus x. Now, similarly, if I do this one, it becomes x, it is x square plus 1, and this becomes 1. Now, this is 0, this is x square plus 1, this is x cube plus x. So, this becomes 1. Now, this becomes x square, this is x, this is x square plus x plus 1, now x plus 1, and this becomes x square plus 1 into this becomes x square plus x. Similarly, this becomes 0, x square plus x. Now, x cube plus x square. So, this becomes x square plus x plus 1. Now, this is 1, this becomes x square plus 1, this is x plus 1. Now, x and this becomes, if I multiply, it will be getting x square, modulo mx we are taking. Now, this is 0, this is x square plus x plus 1. Now, this is x square plus 1, because if I multiply x cube plus x square plus x. So, x and x cube will go x square plus 1. So, this becomes x, this becomes 1, x square plus x, this becomes x square and this becomes x plus 1. Now, again if we observe the properties, first other than 0 elements, we see that we have the one multiplicative identity in each row. That means, for all elements I am getting one multiplicative identity is there. And again here also we see that for every row, if we observe that all the elements appear in each row. That means, for every multiplication modulo mx for one element, we are getting all the set of elements, full set of elements. So, multiplicative identity is there. We write this thing is the modulo mx multiplication table. Okay. So, what we observe that first is multiplicative identity exists, and that is equal to 1, and we get also multiplicative inverse, since for each element we are getting multiplicative inverse. Like if we see that, see for 1 it is 1, for x multiplicative identity is x square plus 1, for x plus 1 multiplicative identity is x square plus x, because x plus 1 into x it is 1. So, we will be getting the multiplicative identity, and if we remember that for under modulo mx multiplication, we will see also that it is a closure, since all the full set of elements, we have seen that all the elements are under S. So, it is a closure property. Then associative under because it is polynomial multiplication, that already we have seen, and now we see that it is all and again since it is multiplication of polynomial. So, commutative also. Now, multiplicative identity exists and multiplicative inverse also exists. So, mainly multiplicative inverse is there. So, it is integral domain. Now, it is inverse is there. So, it forms this forms a field. So, what we see that Z 8, that means Z 8 forms a field under modulo modular polynomial arithmetic. Now, we can see the how we can get the we can find the GCD also by this method, since we know that GCD AB equal to 1, that means there will be no factor, we can use that thing. Now, another thing is or sometimes we use in many applications, it is called the residue class, for particularly for modular arithmetic, this is very important. So, we just do that thing, residue class. See, if it is defined normally, that we here mainly that modular arithmetic we use the remainder. So, we can write this that as if a, when a is an integer, earlier we have defined, and a is congruent to r modulo n. So, we can write all r's whose remainder is same, a is congruent r modulo n. So, we can define this as a residue class. So, quickly if I just see, that means if we take residue class modulo 4, if I consider residue class modulo 4, then I can write modulo 0 or class 0, this will be, say if I start with 0, then 0, 4, 8, 12, all the elements I will be getting that are multiple of 4, I will be getting that remainder 0, and here negative also I will be getting minus 4, minus 8, all these elements I will be getting. So, this is my set. Now, if I consider, since modulo 4 means I have only set 0, 1, 2, 3. So, it is 1 if I write, then similarly I can write it will be 5, 4 plus 1, 9, 13, 17 like that, and similarly here minus 3, minus 4 plus 1, minus 7, etc. And I give 2, then it is minus 6, minus 2, 0, 6, 10, 14, 18, I add, and 3 I will be getting similar way minus 5, minus 1, 0, 7, because 7 modulo 4 is 3, then 11, 15, 19 in this way. Now, when I am taking the polynomial, the same thing we can do, that if say if my Sx is 1 plus x square, then I can write, because I am taking the modular Sx. So, I can write similar way, that this 0 is, okay, I take the set, it is 0, 1 plus x square, then x into 1 plus x square, this will be the multiple of 1 plus x square, and my set is x plus 1. So, in this way I will be getting. Similarly, if it is 1, we have to add 1, just the way we have done, 0 plus 1, 1. So, 1 plus x square, this become x plus x square. Now, this x into 1 plus x square plus 1, then this is x plus 1 into 1 plus x square plus 1. In this way, we will be getting and if I continue I can get this is 2, then it is this is 0 1 x, this is polynomial we are taking. So, this is I have to take the x. So, this becomes x. Now, 1 plus x square, this become x square plus 1, then this become x into 1 plus x square plus x, this becomes x plus 1 into 1 plus x square plus x and so on. So, similarly, in this way I can form this residue class, and it is of very important when we do some applications and application area, particularly in cryptography we use, and coding theory also we use this thing. So, we can write the totally similar way, only the we are considering the polynomial is modulo Sx we are doing. So, here we are doing the modulo Sx. So, in this lecture what we see that how we can form the finite field, and even that it is normal modular arithmetic, it is not a field, but using modular polynomial arithmetic it forms a field. So, actually this lecture we have mainly considered the construction of field using modular polynomial arithmetic, and there mainly we have used some concepts, irreducible polynomials as like a prime, and we have taken the remainders when, or the residues now I can take, because just now we have defined the residue class. So, residues when it is divided by that irreducible polynomial, result is divided. So, we have taken. So, with this we finish our finite field and its applications, the finite field lectures, and with this finite field lecture also we actually our discrete mathematics class ends here. I hope that I have tried to explain the basics of discrete mathematics, and it will be of use, and particularly in computer science and mathematics, other branches also, that how it will be used, how the basic mathematics, the discrete mathematics is used. So, this class will be useful to understand all those things. Thank you.